Good morning, guys. My name is Jigar, and my colleague David and I are going to present Sherlock, automated anomaly detector on top of Druid. Uh, this is used for the time series data, anomaly detection in time series data. I'm going to give you a brief introduction about me. So I'm a software engineer at Oath. I have been working there for 1.5 years, and I'm currently working on stream and batch data pipe processing, and also working on automated anomaly detection using Sherlock. Which I'm going to present today, and also working on multi-arm bandit problem in user engagement. And the technologies that I'm currently using are Kafka, Storm, Druid, and the Tranquility Stream pool using Kafka indexing services, HDFS, Hive, Pig, Chef, Kubernetes, and Apache Superset. Next, my colleague David is going to introduce himself.
Morning, guys. I'm David. I work with Jigger at Yahoo/Oath. I also work on big data pipelines. I mostly work on batch instead of stream. And lately, I've also been working on a GDPR data retrieval system at Oath. So let's go into the motivation for why we developed Sherlock. So the first is that there's a lot of instrumentation bugs that can happen, and those affect a variety of business KPIs that are pretty significant. And so we want to detect those things as quick and early as possible to get them fixed. The next is the biggest growth in big data analytics. And so what we've seen is over the past, as we mentioned in the keynotes, we've seen this exponential growth. And with exponential growth in data comes an exponential growth in monitoring requirements to make sure that we ensure data quality as well. We also have a lot of complex user engagement patterns. So nowadays we have a variety of services and sites. And these user behaviors are not trivial to understand. And the final one is a continuous monitoring requirement. So these sites are up 24/7, 365 days a year. And we need to ensure that all of our sites and services are performing properly at all times. So let's go with some of the current practices and challenges that we do for detecting anomalies in time series data. The first is passive monitoring, which is basically just using your eyes and looking at the time series data itself and just visually detecting outliers. So obviously this has a scalability issue. You can only look through so many dashboards in time series before you start going crazy. And so the second technique that we use is thresholding. So that solves one of the problems in that you can automatically look at a lot of time series, but this leads to a lot of false positives because thresholding is not very smart. And you also need to manually configure those thresholds for each individual time series that you're looking at. So it's not very smart. So let's go through some of the methods and technologies that we use with Sherlock in order to solve these problems. So the first is we utilize Druid as our data store and computation. And that's used for easier and faster data aggregation and exploration. The second one that we use for anomaly detection is EGADS. And this allows us to actually learn the seasonality and trends for time series data. So this solves for the complex user engagement pattern problem. And finally, we developed the Sherlock API, which allows us to automate the monitoring and detection of time series in a large scale. And the nice thing is that all these technologies are open source. So now I'll pass on to Jigger to go into some more detail on the technologies.
Hello. OK, so in the previous slides, David talked about all the technologies that we use to solve this problem. And now I'm going to give you the brief introduction about all the technologies, features, and functionality for all the technologies. So in order to detect the anomaly early, we need data first. So early data is the first most requirement to detect the anomaly. So for that, we use Druid. Druid is a data store designed for the sub-second queries on real-time and historical data. It is a distributed and column-oriented data store. And it is used for business intelligence OLAP queries on the event level data. And we use Druid extensively with Apache Superset, which is open source business intelligence tool through which you can query Druid, and it allows you to query Druid using aggregation and post-aggregation queries, and it has a native connector to the Druid. So you can use Apache Superset on top of Druid and create all the dashboard that is required. And Druid also supports the data sketch algorithm. So sometimes what happens in big data, like queries, some queries doesn't scale well because of limitation in, the huge computation requirement and the time also. So in order to address that problem, Druid uses the data sketch algorithms, which are used to compute set cardinalities, frequencies, and the quantiles almost in linear time. And the data sketch library is also open source from Yahoo. It is built in-house. And so using data sketch algorithm, it is scalable to almost trillions of events and petabytes of data and thousands of concurrent users at a time. Next, let's see EGADS. So getting the 100% accuracy in anomaly detection is a hard problem. Sometimes what happens, you get a lot of false positives. So here we use EGADS, that is Extensible Generic Anomaly Detection System, to get more and more optimized, accurate result, very less false positive in anomaly detection. It is open source Java library for anomaly detection for in large-scale time series data. It is built from Yahoo Labs, and it is open source. You can access it from GitHub. So I'm going to talk about the structure of this library. So this library has basically three modules. First module is a time series modeling module. Another second one is anomaly detection module. Third one is alerting module. So in the time series modeling, it uses the historical data to learn the trend and seasonality in the data, and it uses the historical data to model the time series. So basically, it predicts the expected value using the historical data at time t, and then you use those values with anomaly detection module. This module allows you several anomaly detection models for several use cases, like outlier detection, change point detection, and anomalous behavior detection. So these are different kind of scenarios where you use different algorithms. So extreme low density outlier, change point detection, and k-sigma outlier. These are the three main classes for the algorithm that we use. And then in alerting module, we compute the residuals from the predicted time series from the time series module, and we use the anomaly detection module on top of the residuals, and we allow it to learn the thresholds dynamically so that it adapts to the changing patterns and the trend. And it also filters the irrelevant anomalies and gives you the most accurate result. So in the next slide, I'm going to talk about Sherlock. Bringing all the pieces together, like the power of Druid and the accuracy in EGADS, we have the API Sherlock, which allows us to access all these components from one API. So Sherlock is anomaly detection service built on top of Druid. It also uses EGADS to analyze the time series in real time, in batch, both. So it has a cron-style job scheduling module, which allows you to schedule the job every hour, every day, every week, monthly, however you want. And it has a ad hoc anomaly detection API where you can have a Druid query in real time. You can paste the Druid query on the API and just get the result right away for that particular time series in real time. And it also gives you the emailing module, which gives you the email alerts on the jobs that you have put in the Sherlock. And now let's see the architecture of Sherlock. So Sherlock client so Sherlock is basically built in Java. It uses Java's Spark Java Web Framework, and we use Redis as a backend to store the job metadata information and Druid cluster information and all the reports that are generated from the anomaly detection. And we have a job scheduling mechanism inside Redis. So Redis maintains a priority queue based on the next runtime of the job. And so here, uh, Sherlock server polls Redis every 30 seconds for the jobs, and it returns all the jobs that are eligible to run for at a particular time. And then it runs all the job using the query stored with the job metadata, and it modifies the query at the runtime according to the time interval which you are querying at the particular time, and then it queries Druid, gets the data, and then gives you the result of anomaly reports and stores all the reports to the Redis, from where you can access it later on from the Sherlock client API. Okay, so let's see the job lifecycle in the Sherlock. So when Sherlock API calls Redis and asks for the jobs, it returns the eligible jobs from the priority queue, and the job starts at that particular time. It basically modifies the Druid query according to the time interval, granularity, and the frequency input from the user, and then it queries Druid. Druid gives the JSON native JSON response. So each in the response, all the data points are in terms of JSON, where you need to parse the all the possible time series, and then will input all the time series into EGADS one by one, and EGADS run all the time series and spits out the anomalies, and we segregate all the anomalies among all the time series, and we store all the reports in the Redis. And you also get the email alerts as soon as the anomaly comes in the system and in the real time. And okay, so this is the job cycle inside Sherlock for a particular job. Okay, and let's deep dive into how Sherlock processes the Druid query. So here I have a sample Druid query which we use inside Sherlock. So here, when user inputs this query inside Sherlock, it first grabs some of the metadata from the query. So these are the metadata which we get from the query, like which metrics are we computing, what are the group by dimensions for the query, what is the time interval we are running on, and the granularity detail, like what's the granularity for the data, like daily, hourly, weekly, or monthly. And so this is the format of the Druid query. So here I'm going to describe you the aggregation, filters, and the post-aggregation in the upcoming slides. So this is the aggregation feature inside Druid Query. So here we aggregate two fields, basically, field F1 and F2. So you can map this with a SQL query as a aggregating over some data, like using sum on some of the fields, using count distinct on some of the fields. So here theta sketch is basically the sketching algorithm which we use to compute count distinct for a particular field. And we are using F2 for the theta sketch and long sum on F1. So we get two aggregate field in here, and then we apply filter on top of all the aggregation also. So you can apply the filter using your dimensions and values in here. The type can be and or whatever. So this basically maps to the where clause in SQL. And then in the post aggregation, like after the aggregation, if you still want to compute on top of it, if you want to have some mathematical function on top of the aggregated result. You can still do the post-aggregation functioning over here. So we use F1 field as a metric M1 and F2 field as a metric M2, and we divide both of them, and we get the result for each granularity. And we compute the metric for each granularity, like every day, what's the value of the metric. And so after this, we get the Druid response. So this is the example Druid response for that particular query. Here, I have put only one data point for that response, for the response, because I cannot do all the response over here. So let's say we have a D1 and D2 as a group by dimension we had in the query, right? So let's say we have one cardinality value for D1 and two cardinality values for D2. So there are possible two combinations of those values. So we get two different time series, basically, based on these values. So V1 D1 and V1 D2, that is one time series, and V1 D1 and V2 D2, that is another time series we want to monitor. So this is the one data point, and such as we get all other data points till 2017, 12, 11. And then we parse this time series using the time series parser, and we give it to the EGADS. Now, this is the pictorial representation in the like what happens inside the EGADS. So the first graph is actual time series that we get from Druid, and the second graph is a predicted time series. So basically, modeled time series from the time series model in EGADS, and then we compute the residuals from both the time series, and we plot all the residuals in here. So we have almost 5 residual errors, and now we use this error and to do the anomaly detection. So basically, here, in order to incorporate like all types of anomalies, EGADS provides a bunch of different anomaly detection algorithms. So first class is a k-sigma sensitivity. Using this type, you can detect outlier. So what we do is we generally model the bell curve on top of all the residuals, and depending on, we learn the sigma thresholds, so basically mean and the variance dynamically using the k-sigma models. And then we threshold on the bell curve, and we remove all the anomalies and give it to the system. So, and another class is detecting the change point. So sometimes what happens, like sometimes seasonality in the time series doesn't change, but the trend in the data might change. Like it gradually increases with the time, gradually decreases with the time with the same seasonality, but still you need to detect the change point, like what's happening in the data, why it is increasing or decreasing gradually. So we use kernel-based density for that, and we use a Kullback-Leibler distance algorithm to detect the change point. Here we do the sliding window over the time series, and we compare all the sliding window with each other, and we compute the KL divergence for all the sliding window and detect the change point for particular time series. And the last class is a density-based sensitivity. So let's say you have hundreds of a server running, and you want to monitor all the server, and you have a metric called the latency of a response in the server. Let's say you have all the 100 time series from all the servers. Now you want to detect which server has a bad latency in it. So you can have all the time series together in this algorithm, and you can apply dbScan algorithm or a k-centered clustering algorithm. So basically, it spits out the anomalous behaving servers like as a different class. And that's how you can detect the anomalous time series. So now, why Sherlock is better? So here we saw the challenges previously, like we need to do the manual monitoring, very large number of false positives, and also the uh, other problems. So all the problems are addressed over here. So it allows you to automatically, periodically monitor the data. So that is automated monitoring. You don't need to monitor any dashboard manually. And then it uses EGADS algorithm. So basically, you will get less false positives, and it learns the trend and seasonality in data. And with the Druid faster aggregation, you get detection learning in real time. So I'm going to do the demo next. Um, oops. Okay. So this is a Sherlock API. So we have a major 4 components in here. One is a flash query, that is ad hoc query. You can put your Druid query in here on the dashboard in here, and you can have a result on the fly. And then another part is the job scheduling. You can have a job scheduling from here. And a Druid cluster, you can add your Druid cluster over here. Also the reports, we have a visualization for the calendar heat in terms of calendar heat map for all the reports. So let's see first the flash query. So here you can choose the Druid cluster from here, like whichever Druid cluster you want to query. Um, so inside Oath we use the superset extensively with the Druid. So this is example matrix in here that has a daily granularity. And here we have a group by dimension as a country, and we have a filter FR. Um, so here you can get the Druid query from this, and you can copy the Druid query from here on the dashboard, and you can paste this Druid query in here to do the anomaly detection. You can choose the granularity for that. I'm choosing it as a day. You can have a detection window, like how fast you want the detection in the time series, basically. So here, let's say 7 days. And this is the K sigma sensitivity parameter. You can have 3 sigma or 2 sigma, depending on your need. So this is basically thresholding the bell curve over here. Let's see the results. So here you can see this is the anomaly data point that is detected over here. So if you see the past data, the value for this particular Friday is almost 2.66 million, and on this particular day it dipped to 1.65 million. So that's the anomalous data point, and here you get the deviation from the expected value also. And here you get the group by dimensions. So if you have a large cardinality, so you can monitor all the country basically by using the group by dimensioning here, and you get the anomaly for all the countries. And let's say I use the 3 sigma sensitivity over here. If I use 2 sigma and query this, I'll get more anomalous data points in here because we lowered the threshold for acceptance of the anomaly. Let's use query with hourly granularity. So this is another matrix, and it has an hourly granularity. Let's do the anomaly detection for this. let's choose hourly granularity, and if I go 7-day back, that would be 168 hours. So here you can see the, I forgot to mention one thing. This graph shows predicted value and the original value. So here you can see in the beginning, it didn't learn the dips in the weekend over here. But as it goes with the time, it learns the deeps in the weekend, and it predicts the values very accurately in here. So basically, this time series has no anomaly in it because it's really smooth with all the day data. And here I have some jobs running in. So you can put your anomaly detection job over here from the new job option. Here you can add your job, paste your Druid query, select your granularity and frequency of the job. And you can also put the visualization URL so that you can look at the particular dashboard later on whenever you get the anomaly. So let's see, I have an anomaly report for this. So this is basically the usual visualization for hourly jobs. So here, this is a day of visualization, like Tuesday, Wednesday, then Thursday. And this is the current day, Monday. So here, you can see these 2 points as anomalous, and if you click on them, you can see the metric deviation over here, and you can directly go to the dashboard also from here. Let's see daily job. So daily job has a visualization in terms of days. So it shows you the past 1 year of data, and there is a anomalous data point in here. You can look at that. So from here, you can add your Druid cluster. You need to add the broker from your Druid cluster, and you can have a time SLA in here. So basically, sometimes what happens in the batch data processing, you don't get the data point in real time, right? So you can add SLA over here. Like if your data is arriving 12 hours late in the Druid cluster, you can add 12 hour over here, so that whenever you Sherlock queries Druid, it basically takes care of that 12-hour lag value, and it allows it to periodically do the anomaly detection. Okay, I think that's it from the demo. And questions? Yeah.
Oh, we have the mics if you want to come, because we're recording, I think.
So you mentioned real-time detection. So
Yeah.
this looked like it was more, these more time series, where there were buckets. One thing that we struggle with is finding stuff like anomalies in real time, like for fraudulent. So if somebody's coming in and hitting our systems fraudulently, we need to know, within, less than 10 seconds.
Okay.
Does this kind of support that?
So basically, the Sherlock API is very lightweight. The model we use are really lightweight. So as long as you have the data in real time in Druid cluster, you can have a job running every 10 seconds and querying Druid cluster every 10 seconds, and it can still give you the anomalous report for every 10-second granularity. Yeah.
I would say, given this architecture, the longest period of time will be your latency ingesting your data into Druid versus Sherlock itself. But it can be done.
Yeah. And also, you can configure the amount of data you want to use for the training, basically, from the Sherlock API. So currently, we use almost 1 month of data for hourly and daily jobs, like previous data to train on. So basically, when it grabs the data from Druid cluster, it queries the previous 30 days of data for any time series. Yeah. Every time when it gets the new data point, it queries the previous 30 days of data, or maybe 30 multiplied by 24 hours of data. Yeah. I'm sorry? I'm not sure. Can you describe me the step function? Yeah. K-sigma sensitivity model, the outlier detection model, can detect the outlier. So basically, sudden changes or the sudden spikes or decreases, it can detect those stuff. Yeah.
It will eventually, so it'll detect the point at which it changes, but eventually if it stays continuous at that elevated level, let's say, it will eventually stop reporting that as an anomaly as that becomes the new norm.
Yeah, and you can also have a configuration in EGADS which tells you that you can drop certain amount of outliers while you are training. Like, let's say you can drop 5% of the outliers while you are training the data. So basically, it drops the anomalous data in the training points itself. Yeah.
Question?
Yeah. So it appeared Sherlock is tightly coupled with Druid, but it seemed EGADS was not tightly coupled with Sherlock. So it's open to other data sets stored in
Yeah,
other
definitely.
Timeseries databases.
Yeah.
So
Yeah,
Sherlock, they both just rely on JSON formatted data. So as long as you can parse that into the EGADS format, you can just plug it in.
And we are planning to add more connectors for other data stores like Druid, not only Druid, but also Google BigQuery and Bard on top of like Druid and also in the future. Yeah.
Okay, that's it.
Okay.
Thank you guys for coming.
Thank you guys for coming to the talk.